Okay. So, first, the TA just told me, okay, the average is 50. Okay. So, but a lot of students, I think like about 10 students, dropped the course already. I mean, well, I should say, they came to me with like the drop course, like paperwork. Okay. So, we will, obviously those students perform very, very poor. Okay. So, I mean, after deducting those students from the list, we will compute like the average again. Okay, and then from there, I will see like what I can do. Okay, my usual approach is that I do not directly increase the score. Okay，我就是讲白一点，就我不直接调分数。Okay, instead, what I can do is that okay, I will give you additional bonus. Like for example, in the final exam, I can give you like depending on like the final the average. As I said, my expected average grade will be around 75. So depending on like how far this average is away from the expected average, I will put those points in the final exam as a bonus for you guys to go. 你了解我的意思吗？就是说我期末的时候我会，就是平常是给你100分嘛，对不对？那我会给超过100分。比如说，如果说到时候，比如说，扣掉那些 drop 的，可能平均55分，那跟70分差个10分，对不对？那我期末会大概多给20到25分的一个 bonus 让你去赚。但是我不会倾向，我的个性倾向，我从来不会直接调整分数。OK， 我是希望同学从，比如说，可能是作业，可能是程式，可能是考试里面去调整，了解的意思 ？OK， so yeah, that's it. So I will give you guys like a fair assessment. Maybe next week. Okay, next week. We may have like we are able to exclude those students who drop this course, and we will calculate the average percentage. Okay. So back to this LCS problem. Okay. So, as I said, okay, you could construct this table from bottom up. 就是从这个 from base cases, you fill out those zeros. For the first row, first column, you fill out those zeros because those are the base cases. And then, okay, you can do like row by row or column by column to fill out this table by making use of the this recursive formula. Okay, there are several advantages of that. First, like conceptually, this is much easier to understand. Okay, once you understand that the recursive formula, I mean, construct this thing from bottom up is conceptually easier. And the second, like you eliminate the necessary or the need of recursive calls, because recursive calls also has overhead, right? So if you pull this by, for example, root major or column major. Basically, like you just write nested root. OK， 就是那个回圈嘛 ，nested root。OK， 两层的回圈 ，you are able to fill out the table easily. Okay, and then you can get this final answer, which is B. Okay, but we're not done here, done yet here. Okay, so once you have this thing, how do we obtain the LCS? These numbers represent the length of LCS, right? The length of LCS. So what I'm asking you is, using this table, when you construct this table, okay, like you could like mark this diagonal, okay, this diagonal mark. You want to probably, make a mark. Okay, for example, this blank comes from this diagonal, meaning that there's a match at the last character. Okay, from these two prefixes. Okay, so this 4 comes from the diagonal 3 plus 1. Okay, so you want to mark those diagonal. Okay, places. But with this information, okay, how do you output the real LCS? Okay, to make the problem more challenging, how do you output all LCS? Remember I told you there are more than one possible LCS, right? How do you do it? Assuming you already have this thing, and assuming you already know where those diagonal happens. Somebody tell me. 有没有人？就看这个 table， 可以大概猜得出来。你们先就只要跟我讲，你有一个 LCS， 怎么样才能一个 LCS？
就是如果它是加1的话，就是它会往上走，然后去取它现在的那个代码，然后就一路从上来。
Yes. Cool. That's true. Yeah. So here, okay, this is actually called backtracking. This is also actually called backtracking. So starting from here, okay. So you can go either up or left. You can go either up or left. Okay. Say you go left and you see a diagonal. Okay. If there's no indication at all, you go either up or left. You have 2 ways to go. Okay? But if this break is obtained by adding 1 to a diagonal element, then you have to go diagonal. Okay, you have to go diagonal. Okay, for example, when you go here, because this 4 is obtained from 3 plus 1, so you have to go diagonal. When you go diagonal, that means what? That means you have the match for the last character, and that last character is considered the part of the LCS. So when you go from here to here, okay, that means you will include A as the last character of LCS. So you go here, okay, and then you can go up or left. Okay, say you go left again. Now you have again, like you have to go diagonal again. So this is B, okay, so your output B. And then when you are here, you can go up or left. So if you go left, well, again, you can go up or left. Or should you go left? Well, you have to go diagonal again. So here, you should output A. So, by doing so, okay, so you output the A, B, and A, something like that. And the opposite order. So you should output this to a stack, okay, and then pop the stack out to make sure that it is the output is in the right order. Okay, so that's it. So that's how you obtain one LCS. So how do we obtain all the LCS? How do we obtain all LCS? Remember what I told you, like if there's no indication, like if it's not, this rank is not from the diagonal, you can go either way, right? Now, okay, you branch. You try both branches, like you know. So you remember what you just try this one, right? Sorry, from here we should go up. And then up. Sorry, I made a mistake. Yeah. If it's like, if there's no, if you are not coming from diagonal, you should go like up the bigger part of the two direction. Okay, I made a mistake. So bigger part of these two directions. So for example, you go here, up, and here, up. When you are here, you cannot go back. You have to go up. Because these two comes from the top. Okay, so you go up. And this is we call it the diagonal. So you go here, and this is 1. Okay, you cannot go left. You have to go up because 1 is from the top. So you go left on the diagonal again. Okay, so this is like so this is the thing. Okay, if you go diagonal, there's only one way. If there's no, if this break is not from diagonal, okay, it's from either the top or left. If the top and left have the same value, then you should branch out. You should have a branch for both directions. Okay. But if one of them has a bigger value, so you should take that direction. You know. So basically, so for example, when you are here, this you have 2 4. Okay, top and the left are both 4. So you branch here. And this one you have only one way. And here, I mean, you know, you go left because the left side is bigger. So there's only one way. There's only one way. There's only one way. And there's only one way. There's only one way. Okay, there's only one way. Okay? But when you have a branch here, okay, so you go up, okay, and you have to go diagonal. And here you have to go diagonal. Here you can go either up or left. So now we have to branch out. We have to take this one or this one. You take left, okay, well, you have to go left because 2 comes from left. And you have to go diagonal here, you have to go up. It's 1 come from up. And 1, you have to go diagonal. That's down. So again, this one you go up. Okay, you have to go diagonal, you have to go diagonal, you go down. So you have 3 possible subsequences from here. Okay, each route to the base case will give you LCS. So basically, okay, this backtracking technique, okay, allows you to construct the LCS from this table. Okay. You can reconstruct LCS by tracing back here. So this is one of them. But we should be able to find all the others. So having said that, some diagonal, so you have diagonal here, you have diagonal here. But these 2 diagonal, will never get used in the backtracking. You see, from here you can never reach that, those 2 diagonal. So having diagonal does not mean they have to be, be used in the backtracking. Okay. So for example, here in this one, you see there's no way you can reach there. Because when you can take it back, you go diagonal, you take it back, you go diagonal. And once you are forced to go here, you cannot reach the point here, right? So having diagonal doesn't mean they have to be part of the LCS. It's just like it is like just some marks that help you to identify LCS. So as I said, we will only have like 3 LCS. I think these 2 will not be used. And these 2, this one will not be used. Okay? So constructing the LCS, again, it takes like n times n. Okay. Actually, constructing one LCS, it can take like a minimum n. Why? Because every time, okay, think about this. The only thing you care is go diagonal, right? Go diagonal. And each time you go diagonal, like you are able to construct like you have one character from the LCS, right? And think about this. The LCS, like the longest possible LCS is unique, right? So if you only count the diagonal, that must be equal. It's bounded by equal. Okay. Of course, I mean if I ask you to construct all LCS, that's a different story. Okay. It is going to take a little longer time. Okay, so that's it for diagonal programming. So we still have 20 minutes. So we are going to talk about Woody Allen. Okay, and a little bit of graph here. So probably today we are going to just talk about a little bit of those graph theory, and then next time we'll talk about Allen. Okay, so this is really like a review. Okay, review for your data structure. Supposedly you should have known, you should have learned this from data structure. You know, like for graph, okay, a quadratic graph, or we call it the graph, okay, is represented as GPE. Okay, so order of pair consisting of a set of vertices, okay, and a set of edges, okay, and these edges, okay, they have order because it's a quadratic graph. So if it is on the quadratic graph, the difference is that the edge does not have order, so we can stretch out the order edge. It's still speaking the same edge. So in either case, we have like the edge, number of edges must be bounded by d squared. Okay, and if G is connected, then H must be greater or equal to the number of vertices minus 1. You know that, right? So this, should have been proved in your data structure class. Okay, and so that means that H, okay, the number of H, if you do a log for that, there will be then log. Is bounded is in between b minus 1, the number of annual vertices minus 1 to the b squared. So you get a log. I'm not talking about those are log. Okay. So this is like a big review. And also we are able to use like the adjacency matrix to represent the graph. This is like a big, like a two-dimensional matrix, right? In this matrix, like the matrix size is n times n squared, n represent the number of vertices. And in this matrix, okay, the Aij is 1 if there's an edge between the vertex I and vertex j. Aij is 0 if there's no such edge between vertex I and vertex j. So something like that. And we also can, so this is an example. Okay. So we prefer to use adjacency matrix when the graph is dense. Okay. Because doing so, okay, pretty much like there are a lot of advantage of using adjacency matrix representation. But the storage obviously is an issue. So, but if your graph is dense, well, there's no way you can save space. Okay. So another data structure to represent graph is adjacency list. Okay. For similar, okay, the adjacency list basically like for each vertex, okay, you just include that it's like neighbors in the list. Okay, so this is an example. Okay, so adjacency list is more friendly to sparse graph. Okay, and for unrelated graph, okay, the size of the list, adjacent list, B is the B's degree. Okay, for the related graph, okay, because we only put like the outgoing neighbors in the adjacent list. Okay, so the size of ADJB will be the out degree. So this again, this is a review for the data structure. So handshaking lemma. This is like you know the number of degree. Okay, the total number of degree from all the vertices add up will be 2 times the size of edges. Okay, this is called like handshaking lemma. Okay, for undulating graph, it's like that. For like a undulating graph, it's like out degree, in degree together. Okay, will be 2 times. Okay, something like that. Okay. So doing this, use V plus E is much smaller. So this is a good response for the implementation, as I said earlier. So that's it for the review, okay, of the graph theory. If you want more information for this part, like the graph theory, you need to check like the LCOI is all textbook. Appendix B has a more complete information of the graph theory, but I think that I don't know what you use for the data structure. You can use the data structure to do this. So, okay, only 10 minutes left. Obviously, not a lot of time. So, I will just tell you the problem we are dealing with, and we will do it next time. Okay. The problem is like this. Okay. Given a connected undirected graph, so the graph is connected, and it's undirected. Okay. And each edge has a weight. It's associated with a weight. Okay. So you can sort of like think of it as like, for example, like a network. Like this network is like, we are talking about like a real network. Okay. In between two nodes, like there is like a delay.人都喜欢玩电动玩具，对不对？玩电动玩具不是重视那个 delay 嘛？跟人家在拼的时候，那 delay 比较大的话，你就被人家干掉。So the weight can be associated with the delay. Or like you can imagine this is like each vertex as a major city. For example, like 在台湾的话，就是有台北嘛。台中啊、高雄啊、台南啊这些大城市 ，okay, and the edge represent the highway, okay, and the weight of each edge represent the mileage. 比如台北到台中大概150公里，差不多，对，大概150公里，所以你可以说在台北到台中的。这个age， 它的位置是150之类。So this type of setting, as I said, can be applied to many applications. Okay. So you can, for simplicity, okay, you could assume all age weights are equal. You can assume all age weights are equal. If some age weights are the same, then this problem will have multiple solutions. Okay, so let's assume all the ages have distinct weights. Okay, so if this is the case, okay, a spanning tree, okay, of a graph, okay, represent like a subset of ages. Okay, first it connects all the nodes. with the minimum number of edges. Okay, in other words, if you have, if the number of vertices is n, then you need exactly n minus 1 edges to connect all these n vertices. Okay? And then, okay, when we say minimum spanning tree, I mean like among all the possible spanning tree, we want to find the one with the minimum weight. Okay. When I say minimum weight, I mean like remember I said each spanning tree has some n minus 1 edges, right? So those n minus 1 edges, you add up the weights. That will be the weight of your tree. So I want to find here. We want to find the spanning tree with the minimum weight. Okay? So that's why. That's why. By the way, 这个我要跟大家确认一下，你们data structure 到底讲多少这个东西？你们有教 minimum spanning tree 吗？有还是没有？你们是张老师的还是洪老师的？张老师有讲minimum spanning tree，有讲吗？有讲。如果讲的话，还是我就略过这一章。你觉得？好，我还是讲完这一章，我类似要5分钟。Okay. So we will cover this structure quickly next time. Okay? But the focus will be other stuff like single node, like multiple destination. Okay? And like almost all destination, like short path problem. 你们有学过那个马费的路径？资料结构也有。有人也点头了，教哪边哪个部分，教出来，哪个部分？来耍。啊？有教来耍，有教边门破吗？啊？边门破有3个破回去的。3个破回去。应该是 all day showing path。好，没关系，你们回去查一下，你们资料结构教哪一些？那些我不是不教，但我会教比较快，我会快速带过，好不好？这样子，这样你们下一次我会问你。至少我知道说现在 spanning tree、minimum spanning tree 有教过。那我下一次，这一章完了以后，后面就是那个讲到那个 showing path 的问题。那有三个 chapter 都是3个 lecture 都是在讲 showing path， 所以如果说有一些是教过的，我可以教快一点。你们帮我查一下，好不好 ？OK， 好吧，那这就先到这里。谢谢大家。
后边你们俩就会点。